energy is conserved because the laws of physics are the same today as they were yesterday. Momentum is conserved because those laws work the same here as they do on the other side of the room. Angular momentum is conserved because the universe has no preferred direction. Every conservation law in physics turns out to be a consequence of a symmetry, and that connection was proved in 1915 by a mathematician who was not allowed to hold a professorship, whose work was published under someone else's name, and who died before the world understood what she had found. The mathematician's name was Emmy Noether. She was denied a professorship because she was a woman. She was dismissed from her university because she was Jewish. She died at 53, having produced one of the most important results in the history of science, a result that revealed symmetry as the deepest organizing principle of the physical universe. Tonight, we are going to follow that principle from its origins in ancient geometry, through the palaces of Islamic Spain, where artisans explored it 6 centuries before mathematicians could prove what they had found, through a French prison cell where a 20-year-old transformed it into algebra the night before he was killed in a duel, and into the particle accelerators where it now governs every known particle. The subject is symmetry. The story is how it went from something you can see to something that explains why the universe works. All of it. Slowly. For sleep. Why 6? Why not 5 or 7 or 8? Why should frozen water, which can take any shape it likes, choose this particular symmetry every single time? The answer involves the geometry of water molecules, the angles at hydrogen and oxygen bond, and the way those bonds stack when water crystallizes. But the deeper answer, the one that took mathematicians 3 centuries to formalize, is that 6-fold symmetry is one of only a small number of symmetries that nature permits for repeating patterns on a flat surface. The snowflake doesn't choose 6. 6 is the only option available to it, given the constraints of geometry and physics. That word, symmetry, is the subject of tonight's story. We use it casually to mean balanced, or beautiful, or proportioned. But in mathematics, symmetry has a precise definition, and the precise definition turns out to be one of the most powerful ideas in all of science. Symmetry explains why snowflakes have 6 sides, why there are exactly 17 types of repeating patterns on a flat surface, why energy is conserved, why particles have mass, and why a 20-year-old French mathematician, killed in a duel before he could publish his work, understood something about the structure of equations that the greatest minds of his century had missed. Tonight we are going to follow symmetry from the Greek temples where it meant proportion and beauty, through the Islamic palaces where it became an art form of astonishing complexity, through the prisons and dueling grounds of 19th century France where it became mathematics, and into the particle accelerators of the 20th century where it became the organizing principle of the physical universe. All of it, slowly, for sleep, for sleep. The history of symmetry as a mathematical concept has 3 phases. In the first phase, lasting from antiquity to roughly the 18th century, symmetry was an aesthetic quality, something you could see and admire but not define precisely. In the second phase, from the early 19th century to the early 20th, symmetry became algebra, formalized through group theory into a branch of mathematics with definitions, theorems, and proofs. In the third phase, from the early 20th century to the present, symmetry became physics, recognized as the organizing principle of the fundamental laws of nature. Each phase built on the one before it, and each one deepened the concept beyond what the previous phase could have imagined. The word symmetry comes from the Greek symmetria, meaning measured together. But in modern mathematics, the concept has a precise and powerful definition that goes far beyond the everyday meaning. In everyday language, symmetry means balanced or proportioned, a vague aesthetic quality. In mathematics, a symmetry of an object is a transformation that leaves the object unchanged. Rotate a square by 90 degrees and it looks identical. That rotation is a symmetry. Reflect a butterfly across its vertical midline and the 2 halves match perfectly. That reflection is a symmetry. Translate a wallpaper pattern by 1 unit to the right and the pattern looks identical. That translation is a symmetry. A symmetry is not a property of a static object. It is an action, a thing you can do to an object that leaves it looking identical as before. The object might be a geometric shape, an equation, a physical system, or an abstract mathematical structure. The transformation might be a rotation, a reflection, a translation, a permutation, or any other operation. What makes it a symmetry is that the object is unchanged afterward. That shift from a vague quality to a precise list of operations is what gives symmetry its mathematical power. Collect all the symmetries of an object together and you get a mathematical structure called a group. The study of groups is called group theory, and group theory is the mathematics of symmetry. A square and a certain molecule can have exactly symmetries, even though one is a shape on paper and the other is a physical object made of atoms. The group captures the symmetry itself, stripped of context. And because the group is the same, anything you prove about the symmetry of the square automatically applies to the molecule. That transferability is what makes group theory so useful. And symmetry appears everywhere, in the laws of physics which don't change when you rotate your laboratory or move it across the room. In the structure of crystals, classified by their 230 possible symmetry types, in quantum particles sorted by how they transform under rotations and reflections. In the theory of equations where the symmetries of the roots determine whether a formula exists. Symmetry is not a niche topic. It is one of the central organizing concepts of all mathematics and all physics, and the story of how it achieved that status is the story we are telling tonight. The Greeks loved symmetry. Their temples, their sculptures, their pottery, their mathematics, all of them reflected deep commitment to proportion, balance, and harmony. The Parthenon in Athens is built on ratios that the Greeks considered perfect, the proportions of its columns calculated to produce an appearance of flawless regularity. Greek sculpture strove for ideal human proportions, each body part in precise mathematical relationship to the others. The Parthenon exhibits a subtle mathematical trick called entasis, a slight outward curvature of the columns designed to counteract the optical illusion that makes straight columns appear to bow inward. The entasis preserves the appearance of perfect symmetry by introducing a deliberate asymmetry. The building looks perfectly straight precisely because it isn't. The Greeks understood that perceived symmetry and actual symmetry are not always identical, and they adjusted their architecture accordingly. Greek pottery used geometric patterns, repeating motifs of lines and curves and angles arranged in symmetrical bands around the vessel. For the Greeks, symmetry was a moral concept as much as a mathematical one. A symmetrical object was a beautiful object, and a beautiful object was a good object. The word symmetria in Greek means measured together, implying that the parts of a whole are in correct proportion to each other. Beauty, proportion, and goodness were linked in Greek thought, and symmetry was the concept that held them together. Plato associated the 5 regular solids, the Platonic solids, with the 5 elements, the tetrahedron with fire, the cube with earth, the octahedron with air, the icosahedron with water, and the dodecahedron with the cosmos. Each solid has a high degree of symmetry, every face identical, every vertex identical, every edge identical. Plato chose them precisely because of their symmetry, which he associated with perfection and with the fundamental structure of reality. The Greek understanding of symmetry was visual and aesthetic. They could see it, admire it, and build with it, but they couldn't define it precisely, couldn't classify it systematically, and couldn't use it as a tool for discovery. Turning symmetry from something you admire into something you can calculate with would take 2,000 years. And when it happened not in Greece but in the Islamic world. The Greek tradition was not alone in its reverence for symmetry. Hindu temple architecture, developed over 2 millennia in India, uses elaborate symmetric patterns based on sacred geometry. The mandala, a symmetric diagram used in Hindu and Buddhist meditation, represents the cosmos through concentric squares and circles arranged with 4-fold or 8-fold rotational symmetry. The Kandaraya Mahadeva temple at Khajuraho, built in the 11th century, exhibits a fractal-like self-similarity in which the overall shape of the temple is repeated at smaller scales in its subsidiary towers and decorative elements. Chinese architecture uses bilateral symmetry as an organizing principle, with the Forbidden City in Beijing arranged along a central north-south axis that divides the complex into symmetric halves. The emphasis on bilateral symmetry in Chinese architecture reflects the Confucian value of harmony and balance, connecting aesthetic symmetry to moral philosophy in a way that parallels the Greek association of symmetry with goodness. Every one of these civilizations found symmetry beautiful, used it in art and architecture, and understood, at some level, that symmetry is not arbitrary, that the patterns they admired reflect something real about the structure of space and the constraints of geometry. The mathematical proof of those constraints would come later, but the intuition was there from the beginning. The Alhambra Palace in Granada, Spain, was built in the 13th and 14th centuries by the Nasrid dynasty, the last Muslim rulers of the Iberian Peninsula. Its walls are covered with tile patterns of extraordinary complexity and beauty, geometric designs that repeat across the surface in intricate, interlocking arrangements of stars, polygons, and arabesques. Islamic art, following religious traditions that discourage the depiction of living figures, developed geometric pattern-making to a level of sophistication that has never been surpassed. The artisans of the Alhambra didn't just create beautiful patterns. They explored the mathematical structure of repeating patterns with a thoroughness that wouldn't be matched by professional mathematicians until the 19th century. A repeating pattern on a flat surface, a wallpaper pattern, has a symmetry group, the set of all the things you can do to the pattern that leave it looking exactly as it was before. You can slide it left or right, you can spin it around a point, you can flip it across a line, you can slide it and flip it at once. Each of these operations leaves the pattern unchanged, and together they form what mathematicians call the symmetry group of the pattern. In 1891, the Russian crystallographer Evgraf Fedorov proved that there are exactly 17 distinct wallpaper groups. 17 fundamentally different types of symmetry that a repeating pattern on a flat surface can have. Not roughly 17, but exactly 17. Every repeating pattern that has ever been created or ever will be created belongs to one of these 17 types. The simplest type has only translational symmetry. The pattern repeats when shifted, but has no rotational or reflective symmetry. The most complex types combine rotational symmetry of various orders, twofold, threefold, fourfold, or sixfold, with reflections and glide reflections in multiple directions. Fivefold rotational symmetry is conspicuously absent from the list. You cannot tile a flat surface with regular pentagons. The angles don't fit, pentagons leave gaps or overlaps, and no amount of cleverness can make them tile the plane. This is why fivefold symmetry never appears in wallpaper patterns, in floor tiles, or in crystal structures. It is geometrically forbidden, or so everyone thought until 1974, when the mathematician Roger Penrose discovered a set of two tiles that can cover the plane without repeating. Penrose tilings have fivefold symmetry locally. Small regions of the tiling display fivefold patterns, but the tiling as a whole never repeats. It extends to infinity without ever exactly duplicating itself. Penrose tilings are aperiodic, ordered but not periodic, symmetric locally but not globally. In 1984, the materials scientist Dan Shechtman discovered a physical material, an aluminum-manganese alloy, whose diffraction pattern showed fivefold symmetry. The material, called a quasicrystal, has atomic arrangements that follow Penrose tiling-like patterns. Shechtman's discovery was initially met with disbelief and hostility. The chemist Linus Pauling reportedly said, "There is no such thing as quasicrystals, only quasi-scientists." Shechtman was asked to leave his research group. He persisted, and in 2011 he received the Nobel Prize in Chemistry for his discovery. The mathematical object that Penrose invented as a curiosity turned out to describe a real material that nobody had suspected could exist. The remarkable thing about the Alhambra is that its artisans, working 6 centuries before Fedorov's proof, created examples of all 17 types. Whether they knew there were exactly 17 or whether they simply explored every possibility through artistic intuition and trial and error is unknown. What is known is that the complete mathematical classification of planar symmetry is displayed on the walls of a 14th century palace, created by craftsmen who had no formal mathematical training and no concept of group theory. If you are drifting, let the patterns settle behind your eyes. 17 types of symmetry on a flat surface, stars and polygons and arabesques, repeating forever in every direction, each pattern a different combination of rotation, reflection, translation, and glide reflection. The artisans found them all. The mathematicians proved there were no more. The classification of wallpaper groups is connected to a deeper question. Why 17? Why not 16? Or 18? Or 18? The answer lies in the constraints of geometry. A repeating pattern must tile the plane without gaps or overlaps, and the rotational symmetries compatible with this requirement are limited. Only two-fold, three-fold, fold, and six-fold rotational symmetries are possible. Five-fold and seven-fold are both forbidden. Any order higher than 6 is forbidden. The allowed rotation orders, combined with the possible reflection and glide reflection symmetries, produce exactly 17 distinct combinations. The proof involves enumerating all possible combinations of lattice types, rotation orders, reflection axes, and glide reflections, and showing that each combination either leads to one of the 17 groups or is geometrically impossible. The enumeration is tedious but complete, and the result is one of the cleanest classification theorems in all of mathematics. A finite, exact, exhaustive list of all possible symmetry types for repeating patterns on a flat surface. The analogous classification in 3 dimensions, the space groups, produces exactly 230 types. Every crystal in the universe belongs to one of these 230 groups, and the classification determines many of the crystal's physical properties, its optical behavior, its electrical conductivity, its response to stress and strain. Crystallography, the science of determining crystal structures, depends fundamentally on the space group classification. The classification of symmetry groups in 4 dimensions has also been completed, producing 4,894 types. In higher dimensions, the number of symmetry types grows rapidly, but the principle remains identical. The symmetries of repeating patterns in any number of dimensions can be completely classified, producing a finite list that constrains what is geometrically possible. The mathematical study of symmetry begins with a question about equations. Not about geometry or patterns or tiles, but about equations. And the story of how symmetry became mathematics is one of the most dramatic and tragic stories in the history of the subject. The quadratic formula, known since antiquity, solves any equation of degree 2. Given x squared plus bx plus c equals 0, the formula produces the solutions. In the 16th century, Italian mathematicians discovered formulas for equations of degree 3, the cubic, and degree 4, the quartic. The formulas are more complicated than the quadratic formula, but they exist, and they work, and they produce exact solutions using only addition, subtraction, multiplication, division, and the extraction of roots. So the obvious question was whether you could do the same thing for degree 5. Mathematicians searched for centuries without finding one. In 1824, the Norwegian mathematician Niels Henrik Abel proved that no such formula exists, that the general quintic equation cannot be solved by any combination of the 4 arithmetic operations and root extraction. Abel proved no formula exists, but he couldn't explain why. What is it about degree 5 that makes it different from degree 4? The answer was discovered by a 20-year-old Frenchman named Évariste Galois, and the answer is symmetry. Galois was born in 1811 in Beurre-la-Reine, a small town near Paris. He showed mathematical talent early, but was a difficult student, bored by routine instruction and impatient with teachers who couldn't keep up with him. He applied twice to the École Polytechnique, the most prestigious scientific institution in France, and was rejected both times, reportedly because the examiners couldn't follow his reasoning. He submitted 2 papers to the French Academy of Sciences. The first was lost by Augustin Louis Cauchy, one of the leading mathematicians of the era, who either misplaced it or failed to appreciate its significance. The second was sent to Joseph Fourier, the secretary of the Academy, who died before reading it. The paper was never found. Galois submitted a third paper, which was rejected by the referee, Simeon Denis Poisson, who wrote that it was incomprehensible. 3 submissions, 3 failures, not because the mathematics was wrong, but because nobody could understand it. The rejection by the mathematical establishment intensified Galois' bitterness and his commitment to radical politics. He enrolled instead at the École Normale Supérieure, a lesser institution, where he continued to develop his mathematical ideas in near-total isolation. Galois' political activities, he was a committed Republican in a period of monarchist restoration, led to his arrest and imprisonment in 1831. He was 20 years old. In prison, he continued to work on mathematics, developing the theory that would bear his name. After his release, he became involved in a dispute whose exact nature has never been fully established, possibly romantic, possibly political, that resulted in a challenge to a duel. The night before the duel, knowing he might not survive, Galois sat down and wrote a letter to his friend Auguste Chevalier, summarizing his mathematical discoveries. The letter is one of the most remarkable documents in the history of mathematics. In a few frantic pages scribbling "I have no time" in the margins, Galois outlined a theory that would take other mathematicians decades to understand, and that would transform algebra, geometry, and number theory permanently. On the morning of May 30th, 1832, Galois fought the duel. He was shot in the abdomen and left on the ground. A passing farmer found him and took him to a hospital, where he died the next day. He was 20 years old. Galois's manuscripts were given to his friend Chevalier, who passed them to the mathematician Joseph Louville. Louville spent 14 years studying them before publishing them in 1846, with the comment that the manuscripts contained results of the highest importance. The delay was not negligence. The mathematics was so far ahead of its time that Louville needed years to understand it. Even after publication, Galois's ideas spread slowly. Camille Jordan's Traité des substitutions et des équations algébriques, published in 1870, was the first systematic treatment of group theory, nearly 40 years after Galois's death. By the end of the 19th century, group theory had become one of the central branches of mathematics, and Galois was recognized as its founder. His story, the mathematical genius dying in a duel at 20, became one of the great legends of mathematics, retold in every generation, cited as evidence that mathematical brilliance can appear anywhere, at any age, and that the institutions designed to recognize talent can fail spectacularly. The tragedy of Galois' life is compounded by the question of what he might have done if he had lived. He was 20 when he died. He had already invented group theory. He had already answered the question of which equations can be solved by formula. He had already seen deeper into the structure of algebra than anyone alive. What would he have done at 30, at 40, at 60? The question has no answer, but the asking of it is itself a measure of his achievement. Very few mathematicians inspire that question. Galois does, because what he accomplished in 20 years of life was enough to occupy the rest of mathematics for the next 2 centuries. What Galois discovered in the months before his death is that the solvability of an equation is determined by the symmetry of its roots. The roots of an equation, the values of x that make it true, can be rearranged, permuted, swapped with each other in ways that preserve certain algebraic relationships. The set of all such permutations forms a mathematical structure that Galois called a group. A group is just the mathematician's way of making symmetry precise. A group is a set of transformations, together with a rule for combining them, that satisfies 4 properties. Closure, meaning combining 2 transformations produces another transformation in the set. Associativity, meaning the order of combining doesn't matter as long as you keep the sequence. Identity, meaning there's a transformation that does nothing. And invertibility, meaning every transformation can be undone. The symmetries of a square form a group. The transformations are do nothing, rotate 90 degrees, rotate 180 degrees, rotate 270 degrees, reflect across the horizontal axis, reflect across the vertical axis, reflect across one diagonal, reflect across the other diagonal. 8 transformations in total. Combining any 2 produces another one in the set. The identity is do nothing. Every transformation can be undone by applying it again or applying its reverse. The 8 symmetries of a square form a group with 8 elements, called the dihedral group of order 8. An equilateral triangle has 6 symmetries, 3 rotations, 0 degrees, 120 degrees, and 240 degrees, and 3 reflections, 1 across each altitude. These 6 symmetries form the dihedral group of order 6. A circle has infinitely many symmetries, every possible rotation and every possible reflection. Its symmetry group is continuous rather than discrete, and it is the simplest example of a Lie group. The symmetries of a molecule determine its chemical properties. Chemists use group theory to predict which molecular vibrations are active in infrared spectroscopy, which electronic transitions are allowed, and how a molecule will interact with polarized light. The application of group theory to chemistry, developed in the 20th century, transformed spectroscopy from an empirical art into a predictive science. The symmetries of a crystal determine its physical properties. The 230 space groups, the three-dimensional analogues of the 17 wallpaper groups, classify every possible crystal structure. Every mineral, every metal, every semiconductor, every salt crystal belongs to one of these 230 groups. X-ray crystallography, which determines the atomic structure of crystals by analyzing the diffraction of X-rays, depends on the symmetry classification to interpret its data. The connection between symmetry and crystallography deserves deeper attention because it represents one of the most practically important applications of group theory in the history of science. A crystal is a solid in which atoms are arranged in a repeating three-dimensional pattern. The symmetry of that pattern determines virtually every physical property of the crystal. Whether the crystal is transparent or opaque, whether it conducts electricity or blocks it, whether it is hard or brittle, how it bends light and how it handles heat. All of these properties trace back to one thing, the symmetry group of the crystal's atomic arrangement. X-ray crystallography, developed in the early 20th century by Max von Laue and William and Lawrence Bragg, uses the diffraction of X-rays to determine the atomic structure of crystals. When X-rays pass through a crystal, they scatter off the atoms and produce a diffraction pattern, a pattern of bright and dark spots that encodes the positions of the atoms. Interpreting the diffraction pattern requires knowing the symmetry group of the crystal, because the symmetry determines which diffraction spots are present and which are absent. The symmetry is the key that unlocks the atomic structure. The determination of the structure of DNA by James Watson and Francis Crick in 1953 relied on X-ray crystallography data obtained by Rosalind Franklin. Franklin's X-ray diffraction images of DNA showed a distinctive cross-shaped pattern that indicated a helical structure with specific symmetry properties. The symmetry of the diffraction pattern revealed the symmetry of the molecule, and the symmetry of the molecule constrained the possible arrangements of atoms, leading Watson and Crick to the double helix. The structure of hemoglobin, the protein that carries oxygen in your blood, was determined by X-ray crystallography by Max Perutz, who spent 22 years on the problem and received the Nobel Prize in 1962. The structure of insulin was determined by Dorothy Hodgkin, who also received a Nobel Prize. The structure of the ribosome, the molecular machine that translates genetic information into proteins, was determined by X-ray crystallography and earned the Nobel Prize in 2009. Each of these determinations depended on the group-theoretic classification of crystal symmetries, a classification completed by mathematicians in the 1890s for reasons entirely unrelated to biology. The connection between abstract mathematics and biological discovery is one of the most striking examples of what Eugene Wigner called the unreasonable effectiveness of mathematics. The 230 space groups were classified as a mathematical exercise, a complete enumeration of the possible symmetries of repeating patterns in three-dimensional space. Nobody imagined that the classification would be used to determine the structure of the molecule that carries the genetic code, or the protein that carries oxygen, or the machine that translates genes into proteins. The mathematics anticipated the science by half a century, and the science could not have progressed without the mathematics. Symmetry also governs the behavior of waves in crystals, including the quantum mechanical waves that describe electrons. The theory of electronic band structure, which explains why some materials are conductors, some are insulators, and some are semiconductors, depends on the symmetry of the crystal lattice. The symmetry determines which energies are available to electrons and which are forbidden, creating bands of allowed energies separated by gaps of forbidden energies. Semiconductors have a small band gap, which is what makes them useful for building transistors and integrated circuits. The entire semiconductor industry, which produces the chips that run every computer and every phone, depends on the band theory of solids, which depends on the symmetry classification of crystal lattices. The mathematician who proved that there are exactly 230 space groups, Evgraf Fedorov, was a Russian crystallographer working in the 1890s. He could not have imagined that his classification would underpin an industry worth trillions of dollars. But the mathematics doesn't care about applications. It classifies what is possible, and the applications follow when someone needs to know what is possible. The relationship between symmetry and technology extends beyond semiconductors. Liquid crystals, used in flat panel displays, are materials whose molecular arrangement has a specific symmetry that can be changed by applying an electric field. The change in symmetry changes the optical properties of the material, allowing individual pixels to be turned on and off. The physics of liquid crystals is the physics of symmetry and symmetry breaking, applied at the molecular level to create the screens you look at every day. Fiber optics, which carry most of the world's internet traffic, exploit the cylindrical symmetry of glass fibers to guide light over long distances with minimal loss. The waveguide modes, the patterns of light that can propagate through the fiber, are determined by the fiber's symmetry, and the design of modern fiber optic systems uses the group theory of cylindrical symmetry to optimize signal transmission. Even the encryption that protects your online communications depends on symmetry. The RSA encryption algorithm, which secures most internet transactions, relies on the difficulty of factoring large numbers into primes. The mathematical structure underlying the algorithm involves modular arithmetic, which has a group structure. The security of the encryption depends on properties of these groups, specifically the difficulty of computing discrete logarithms in certain groups. Group theory, the mathematics of symmetry, protects your passwords and your credit card numbers every time you make an online purchase. These connections between symmetry and technology are mathematical, not metaphorical. The group theory that Galois invented in a prison cell, that Lie extended to continuous transformations, that Noether connected to conservation laws, that physicists used to build the Standard Model, is that group theory that crystallographers use to determine molecular structures, that electrical engineers use to design semiconductors, that computer scientists use to encrypt data. One theory invented for one purpose, applicable to all of them, the unity of mathematics, expressed through symmetry, made physical in technology. The structure of DNA was determined by X-ray crystallography, using the symmetry of the double helix to constrain the possible arrangements of atoms. Consider the equation x to the fourth minus 1 equals 0. The roots are 1, -1, I, and -I, the four roots of unity. These roots can be permuted in 24 ways, but not all permutations preserve the algebraic relationships between them. The permutations that do preserve the relationships form the Galois group of the equation. For this particular equation, the Galois group is the cyclic group of order 4, which has the property of solvability. Therefore, the equation can be solved by formula, and indeed it can. The solutions are simply 1, -1, I, and -I. For the general quintic, the Galois group is the symmetric group on 5 elements, which has 120 elements. This group is not solvable. It lacks the specific structural property that solvability requires. The lack of solvability is not a deficiency of human ingenuity. It is a structural feature of the group itself. No formula exists because the group forbids it, and the group forbids it because its internal structure is too complex, too tangled, too unbreakable to decompose in the way that solvability requires. The brilliance of Galois's insight is that he reduced the question, can this equation be solved, to a question about the structure of a group, and the group structure question can be answered by purely algebraic methods, without any reference to the original equation. The equation lives in the world of numbers. The group lives in the world of symmetry, and the answer to the number question is determined by the symmetry structure. Algebra and symmetry are linked permanently and exactly through Galois's theory. The first time I truly understood what Galois had done, I sat at my desk for a long time without moving. A 20-year-old, in prison, with no mentor, no collaborators, no library, had looked at the problem of solving equations and seen that the answer lay not in the equations themselves, but in their symmetries. He had invented an entirely new branch of mathematics, group theory, as a tool for answering a specific question, and the tool turned out to be more important than the question. Group theory is now one of the central branches of modern mathematics, used in every area from number theory to topology to physics. And its inventor died in a duel before he turned 21, leaving behind a letter and a handful of manuscripts that nobody understood for 14 years. The connection between symmetry and conservation goes even deeper when you consider what happens when symmetry is approximate rather than exact. An approximate symmetry leads to an approximately conserved quantity, a quantity that changes slowly rather than remaining constant. In particle physics, isospin symmetry, the approximate symmetry between the up quark and the down quark, leads to the approximate conservation of isospin in strong interactions. The symmetry is not exact because the up and down quarks have slightly different masses, and the small difference in masses produces small violations of isospin conservation. Approximate symmetries are ubiquitous in physics and remarkably useful. They allow physicists to make predictions that are nearly correct, and then compute corrections systematically. The technique of perturbation theory, which starts from a symmetric situation and adds small symmetry-breaking effects as corrections, is one of the most powerful computational methods in all of physics. The standard model's predictions, which agree with experiment to extraordinary precision, are computed using perturbation theory around symmetric starting points. The philosopher of science Pierre Curie articulated a principle in 1894 that connects symmetry to physical phenomena. The symmetries of the cause must be found in the effect. If a cause has a certain symmetry, the effect must have at least that symmetry. A perfectly symmetric cause can produce a symmetric effect or a less symmetric effect through symmetry breaking, but it cannot produce an effect with more symmetry than the cause. Symmetry can be broken but not created. Curie's principle has been applied to everything from crystal growth to cosmology. The large-scale isotropy of the cosmic microwave background radiation, its near-identical temperature in every direction, reflects the high symmetry of the early universe. The small deviations from isotropy, the tiny temperature fluctuations that seeded the formation of galaxies, reflect the small symmetry-breaking perturbations that grew over billions of years into the structures we see today. The interplay between symmetry and symmetry breaking is the central theme of modern fundamental physics. The laws are symmetric, but the solutions break the symmetry. The universe exists in the space between perfect symmetry and total chaos, in the zone where enough symmetry is present to create structure and enough symmetry is broken to create variety. Too much symmetry, and the universe is a featureless void. Too little, and it is random noise. The universe we inhabit is the mathematically narrow region between the two, the region where structure, complexity, and life are possible. This insight that existence requires the breaking of symmetry is one of the most profound ideas in all of physics. It means that the universe could not have remained in its initial symmetric state. The symmetries had to break. The ball had to roll off the hill, and the direction it rolled, the particular way the symmetry broke, determined everything that followed. Every particle, every atom, every star, every living thing. We exist because symmetry broke, and the way it broke determined what we are. The word group was first used in its mathematical sense by Galois himself, in the letter he wrote the night before his duel. The concept was implicit in the work of earlier mathematicians, particularly Lagrange, who had studied the permutations of roots of equations in the 18th century. But Galois was the first to define the concept explicitly, to recognize its central importance, and to use it as a tool for answering questions that had resisted every other approach. The development of group theory after Galois followed two parallel paths. The first, pursued by Cauchy, Jordan, and Silo, developed the theory of finite groups, the groups with a finite number of elements. The second, pursued by Lie, Killing, and Cartan, developed the theory of continuous groups, the groups with infinitely many elements parameterized by continuous variables. The two paths converged in the 20th century when representation theory provided a common language for both finite and continuous groups, and when physics demanded the use of both. Arthur Cayley's theorem, proved in 1878, says that every group can be represented as a group of permutations, a group of rearrangements of some set. This result means that group theory is, at bottom, the study of rearrangements, the study of the different ways a set of objects can be shuffled while preserving structure. The connection to symmetry is clear. A symmetry of an object is a rearrangement of the object's parts that leaves the object unchanged. Cayley's theorem confirms that this intuition is correct, that every group is a symmetry group of some structure. Symmetry and groups are now so tightly intertwined that mathematicians use the words almost interchangeably. They are two perspectives on one mathematical reality, and that reality is among the deepest in all of mathematics. The applications of group theory extend far beyond physics and chemistry. In computer science, group theory underlies the theory of error-correcting codes, which allow data to be transmitted reliably over noisy channels. In genetics, group theory has been used to model the structure of the genetic code. the assignment of 64 codons to 20 amino acids plus a stop signal. In music theory, group theory describes the structure of scales, chords, and rhythmic patterns. In linguistics, the symmetries of grammatical structures have been analyzed using group theoretic methods. In economics, game theory uses group theory to analyze symmetric games, games in which the players are interchangeable. The universality of group theory is a consequence of the universality of symmetry. Structure implies symmetry, symmetry implies a group, and a group opens the door to every tool that group theory provides. The subject that Galois invented in a prison cell at the age of 20 has become one of the most widely applicable branches of all mathematics, touching every field that deals with pattern, structure, or transformation. Now, Galois' groups were finite. The symmetries of a square, of a triangle, of an equation's roots are all finite groups with a finite number of elements, but symmetry also comes in continuous flavors. And the mathematics of continuous symmetry was developed by the Norwegian mathematician Sophus Lie in the 1870s and 80s. Continuous symmetry is fundamentally different from discrete symmetry. The symmetries of a square are discrete. There are exactly 8 of them, and you can list them all. The symmetries of a circle are continuous. There are infinitely many, parameterized by a continuous variable, the angle of rotation. You can rotate a circle by 1 degree, by half a degree, by 1,000th of a degree, by any amount whatsoever. The rotations form a continuum, a smooth family parameterized by a real number. This smoothness has profound mathematical consequences. A continuous symmetry group has a tangent space at the identity, a linear approximation to the group near the transformation that does nothing. This tangent space is called a Lie algebra, and it captures the local structure of the group in a linear algebraic form. The relationship between a Lie group and its Lie algebra is analogous to the relationship between a curved surface and its tangent plane. The tangent plane is a linear approximation, simpler than the surface itself, but it captures enough information to reconstruct the surface locally. Lie algebras can be classified using linear algebra, which is much simpler than the non-linear geometry of the groups themselves. The classification of Lie algebras, and through them the classification of Lie groups, is one of the great achievements of 19th and 20th century mathematics. It reveals that the world of continuous symmetry, which seems at first to be unlimited in its variety, is actually highly constrained. Only certain types of continuous symmetry are mathematically possible, and the possible types are completely classified. Consider the symmetries of a circle. You can rotate a circle by any angle, not just by 90 degrees or 60 degrees, but by any amount, 1 degree, half a degree, 1,000th of a degree, and the circle looks identical. The set of all rotations of a circle forms a group, but it's a continuous group, a group with infinitely many elements, one for every possible angle. Lie studied these continuous symmetry groups, now called Lie groups, and developed a theory that connects continuous symmetry to calculus and differential equations. Lie groups turn out to be the natural language for describing the symmetries of physical laws. The laws of physics don't just have discrete symmetries like the eightfold symmetry of a square. They have continuous symmetries like the rotational symmetry of empty space. You can rotate your laboratory by any angle and the laws of physics are unchanged. You can move your laboratory to any location and the laws are unchanged. You can perform your experiment today or tomorrow and the laws are unchanged. These continuous symmetries, translational symmetry, rotational symmetry, time translation symmetry, form Lie groups. Lie groups are classified by their structure, and the classification, completed by Wilhelm Killing and Elie Cartan in the late 19th and early 20th centuries, reveals a surprisingly small number of types. There are 4 infinite families of classical Lie groups corresponding to rotations, unitary transformations, symplectic transformations, and orthogonal transformations, and there are 5 exceptional Lie groups called G2, F4, E6, E7, and E8, which don't fit into any family and whose existence depends on specific numerical coincidences in the theory of Lie algebras. The exceptional groups are among the most mysterious objects in mathematics. E8, the largest of them, has 248 dimensions and a structure so complex that its full description wasn't computed until 2007, when a team of mathematicians using a supercomputer completed a calculation that would have taken a single computer roughly the age of the universe. E8 appears in string theory as the symmetry group of one version of the theory, and its appearance suggests that the deepest symmetries of the physical universe may involve mathematical objects of extraordinary complexity. The Lie group classification also constrains the possible symmetries of physical laws. The standard model uses the groups U1, SU2, and SU3, grand unified theories, which attempt to combine the three forces of the standard model into one, typically use larger groups like SU5, SO10, or E6. The choice of group determines the predictions of the theory, including which particles exist, which forces act, and which conservation laws hold. The mathematics constrains the physics, and the constraints come from the classification of Lie groups, a purely mathematical result with no input from experiment. Sophus Lie was born in Nordfjordeid, Norway, in 1842, in a country with no tradition of advanced mathematical research. He studied at the University of Christiania, now Oslo, and travelled to Germany and France to learn from the leading mathematicians of the era. His mathematical style was geometric and intuitive rather than algebraic and rigorous, and his papers were often difficult for other mathematicians to follow. Lie's key insight was that many of the differential equations that arise in physics and geometry have symmetries, and that these symmetries can be exploited to simplify and solve the equations. A differential equation might be symmetric under rotations, or under translations, or under scaling. Each symmetry reduces the complexity of the equation, and if enough symmetries are present, the equation can be solved completely. The connection between symmetry and solvability in differential equations parallels the connection that Galois discovered between symmetry and solvability in algebraic equations. In both cases, the symmetries of the equation determine whether it can be solved, and the group of symmetries provides the tool for solving it. Galois worked with finite groups and algebraic equations. Lie worked with continuous groups and differential equations. The parallel between their theories is one of the deepest structural analogies in mathematics. Lie's work was not fully appreciated during his lifetime. He suffered from depression and physical illness in his later years, and he died in 1899 at the age of 57, leaving behind a body of work that would take decades to organise, clarify, and extend. The theory of Lie groups and Lie algebras as it exists today was largely developed by Élie Cartan, Hermann Weyl, and Claude Chevalier in the early 20th century, building on Lie's foundations. Weyl, in particular, was responsible for connecting Lie group theory to physics. In his 1929 book, The Theory of Groups and Quantum Mechanics, Weyl showed that the symmetry groups of quantum systems are Lie groups, and that the representation theory of these groups, the study of how they act on vector spaces, provides the mathematical framework for quantum mechanics. Weyl's work established the connection between group theory and physics that would lead, decades later, to the Standard Model. The representation theory of groups is itself a rich and deep subject. A representation of a group is a way of associating each group element with a matrix, so that the group operation corresponds to matrix multiplication. Representations allow abstract symmetries to be realized concretely as transformations of vectors in a specific vector space. The study of representations reveals the internal structure of the group and connects it to linear algebra, analysis, and geometry. Every elementary particle in the Standard Model is classified by its representations under the gauge groups SU3, SU2, and U1. The electron is a specific representation of these groups. The quark is a different representation. The photon is yet another. The properties of each particle, its charge, its mass, its interactions with other particles, are determined by its representation. The representation is the particle in a very precise mathematical sense. To know the particle is to know its representation, and to know its representation is to know its symmetry. This is the deepest connection between symmetry and physics. The fundamental constituents of matter are not things. They are representations of symmetry groups. The universe is not made of stuff. It is made of symmetry. And the mathematics of symmetry, group theory, is the language in which the universe writes itself. And here is where symmetry connects to physics in the deepest possible way. In 1915, the German mathematician Emmy Noether proved a theorem that links every continuous symmetry of a physical system to a conserved quantity, a quantity that doesn't change over time. Noether was one of the most important mathematicians of the 20th century and one of the most under-recognized. She was denied a proper academic position for years because she was a woman. When she lectured at the University of Göttingen, the mathematics faculty had to list her courses under David Hilbert's name because the university regulations didn't allow women to lecture. She was dismissed from her position when the Nazis came to power because she was Jewish. She fled to the United States and died in 1935, at the age of 53. Emmy Noether's personal story deserves a longer telling, because it illuminates both the power of symmetry and the obstacles that mathematical genius has sometimes faced. Noether was born in Erlangen, Germany in 1882, the daughter of the mathematician Max Noether. She studied mathematics at a time when women were not officially admitted to German universities. She was allowed to audit courses but not to enroll. She completed her doctorate in 1907 under the supervision of Paul Gordon with a thesis on algebraic invariant theory. After completing her doctorate, Noether worked at the University of Erlangen without pay for 7 years. In 1915, Hilbert and Klein invited her to Göttingen, the world's leading center for mathematical research. The philosophy faculty objected to her appointment on the grounds that she was a woman. Hilbert's response has become famous. "I do not see that the sex of the candidate is an argument against her admission as private docent. After all, the Senate is not a bathhouse." Despite Hilbert's support, the appointment was denied. She lectured for 4 years under Hilbert's name before receiving her own appointment in 1919. At Göttingen, Noether developed the abstract algebraic methods that would transform the field. Her approach, focusing on abstract structures, on rings and ideals and modules rather than on specific calculations, was revolutionary. She taught a generation of students who spread her methods throughout mathematics. Her influence is so pervasive that the term Noetherian, used to describe mathematical structures satisfying a specific finiteness condition, appears in virtually every textbook on algebra. When the Nazis came to power in 1933, Noether was dismissed from her position along with all other Jewish faculty. She emigrated to the United States and took a position at Bryn Mawr College in Pennsylvania. She continued to work and to teach until her sudden death from surgical complications in April 1935. At the age of 53, Einstein wrote in a letter to the New York Times, "In the judgment of the most competent living mathematicians, Fraulein Noether was the most significant creative mathematical genius thus far produced since the higher education of women began." The tribute was accurate and, in its qualified phrasing, revealing of the era in which it was written. Noether's theorem, the result for which she is most famous outside of mathematics, was proved in 1915, identical year she arrived at Göttingen. The theorem was motivated by questions in general relativity that Einstein and Hilbert had been unable to resolve. Noether solved the problem in a few pages, producing a result of such generality and such depth that it transcended the specific physical question that motivated it. The theorem belongs not to physics, but to mathematics, and its applications extend to every branch of physics that has symmetry, which is to say every branch of physics. Her theorem says something so simple, it almost sounds obvious, until you realize nobody had ever proved it. If the laws of physics don't change over time, then energy is conserved. Energy is conserved because physics doesn't change over time. The symmetry of space, the fact that the laws of physics are here what they are over there, implies the conservation of momentum. Momentum is conserved because physics doesn't change from place to place. The symmetry of rotation, the fact that the laws of physics don't depend on which direction you face, implies the conservation of angular momentum. Before Noether, these conservation laws were separate empirical facts, observed and unexplained. After Noether, they were all instances of one principle. Symmetry implies conservation. Every conservation law in physics corresponds to a symmetry. Every symmetry produces a conservation law, gauge symmetry, a more abstract kind of symmetry involving the internal degrees of freedom of quantum fields, implies the conservation of electric charge. The conservation of baryon number, lepton number, and other quantum numbers all correspond to specific symmetries of the Standard Model. When physicists discover a new conservation law, they look for the corresponding symmetry. When they identify a new symmetry, they predict the corresponding conservation law. The two concepts are inseparable. Every symmetry produces a conservation law. The connection is exact, universal, and runs in both directions. Noether's theorem was initially applied to classical mechanics, to the physics of objects you can see and touch, planets and pendulums and spinning tops. But its deepest applications came in quantum field theory, where the concept of symmetry was extended far beyond anything Noether could have imagined. In the 1950s and 60s, physicists developed gauge theories, theories in which the fundamental interactions between particles are determined by local symmetry requirements. A gauge symmetry is a symmetry that can vary from point to point in space. The requirement that the laws of physics respect this local symmetry forces the existence of specific particles called gauge bosons that mediate the interaction. The photon, the particle of light that mediates the electromagnetic force, exists because the laws of electromagnetism have a local U1 gauge symmetry. The photon isn't put into the theory by hand. It emerges automatically from the symmetry requirement. The W and Z bosons, which mediate the weak force, emerge from SU2 gauge symmetry. The gluons, which mediate the strong force, emerge from SU3 gauge symmetry. Every force-carrying particle in the standard model is a consequence of a gauge symmetry. Think about what that means. The particles that carry the fundamental forces of nature exist because of symmetry. They are not independent ingredients of the theory. They are consequences of the theory's structure, forced into existence by the requirement that the laws of physics respect specific symmetry groups. Remove the symmetry and everything disappears: the particles, the forces, the physics itself. Yang and Mills proposed a mathematical framework for non-abelian gauge theories in 1954, generalizing the U1 gauge symmetry of electromagnetism to more complex groups. Their framework, now called Yang-Mills theory, is the mathematical foundation of the entire standard model. The proof that Yang-Mills theory is mathematically consistent, that it produces well-defined predictions at all energy scales, is one of the 7 Millennium Prize problems, with $1 million reward. The theory works, physicists use it every day, but a rigorous mathematical proof of its consistency has not been found. The second time I felt something fundamental shift in my understanding was when I absorbed what Noether's theorem actually means. Conservation of energy isn't a separate fact about the universe, it's a consequence of the universe being consistent over time. The law and the symmetry are one thing, expressed in two languages. I had learned both facts separately, in different courses, taught by different professors. Noether showed they were always one fact. The feeling of two separate ideas collapsing into one is unlike anything else in mathematics, a sudden simplification that leaves the world lighter and slightly strange. If you are still awake, the story goes deeper. We've seen symmetry in tiles, in equations, in physical laws. Now we follow it into the structure of matter itself. The standard model of particle physics, the theory that describes every known particle and 3 of the 4 fundamental forces, is built entirely on symmetry groups. The theory's symmetry group is called SU3 times SU2 times U1, a string of letters and numbers that looks like gibberish but encodes the structure of reality. Each piece of that string corresponds to a fundamental force. U1 is the symmetry group of electromagnetism. It is the group of rotations of a circle, the simplest continuous symmetry group. The conservation of electric charge follows from U1 symmetry through Noether's theorem. Every electron in the universe carries exactly identical electric charge, and the reason is that the laws of electromagnetism have this specific circular symmetry. Cu2 is the symmetry group of the weak nuclear force, the force responsible for radioactive decay. The weak force transforms one type of particle into another, turning up quarks into down quarks and electrons into neutrinos. These transformations are described by the group Su2, the group of 2 by 2 unitary matrices with determinant 1. Cu3 is the symmetry group of the strong nuclear force, the force that holds protons and neutrons together inside atomic nuclei. Quarks come in 3 colors, an arbitrary label that has nothing to do with visible color, and the strong force is symmetric under rotations in this 3-dimensional color space. The symmetry group of these rotations is Su, the 3. The entire standard model, every known particle, every known force except gravity, is a consequence of these three symmetry groups and the way they combine. Physics is symmetry. The laws of nature are the consequences of the symmetries of nature. And the mathematics that describes the symmetries is the group theory that Galois invented in a prison cell in 1831. The Standard Model was constructed over roughly 3 decades, from the 1950s to the 1970s, by physicists including Sheldon Glashow, Abdus Salam, Stephen Weinberg, Murray Gell-Mann, and many others. Each step in the construction involved identifying a symmetry group and deriving its consequences. Gell-Mann's eightfold way, proposed in 1961, classified the known hadrons using the symmetry group SU3 and predicted the existence of a new particle, the omega-baryon, which was discovered experimentally in 1964. The prediction, from pure symmetry considerations of a particle that nobody had observed, is one of the most dramatic confirmations of the power of symmetry in physics. The electroweak theory, developed by Glashow, Salam, and Weinberg in the 1960s and 70s, unified electromagnetism with the weak nuclear force using the symmetry group SU2 times U1. The theory predicted the existence of the W and Z bosons, which were discovered at CERN in 1983. Again, symmetry predicted particles before experiment found them. But the symmetries of the Standard Model are not perfect. If they were, all particles would be massless, traveling at the speed of light, and the universe would be a featureless soup of radiation with no matter, no atoms, no stars, no planets, no people. The universe we live in exists because the symmetries are broken. Symmetry breaking is one of the most important concepts in modern physics. A system has a symmetry, but its lowest energy state does not. The equations obey the symmetry, but the solutions don't. The mathematical analogy is a ball sitting on top of a hill. The hill is symmetric, identical in every direction, but the ball can't stay on top forever. It rolls down, and the direction it rolls breaks the symmetry. The hill has no preferred direction. The ball, once it rolls, does. The symmetry of the hill is real. The breaking is real, and both coexist. A magnet provides another example. The laws of electromagnetism have rotational symmetry, no preferred direction. But a bar magnet has a north pole and a south pole, a definite orientation in space. The symmetry of the laws is broken by the ground state of the magnet. Heat the magnet above its Curie temperature and the magnetization disappears. The symmetry is restored, cool it back down, and the magnetization returns, pointing in some direction, breaking the symmetry again. The direction it chooses is random. Any direction is equally likely, but once chosen, it persists. The symmetry breaks spontaneously. Water provides a simpler example. Liquid water has rotational symmetry. It looks identical from every direction. Ice crystals do not. They have six-fold symmetry, a specific crystallographic structure that picks out specific directions. Freezing breaks the rotational symmetry of the liquid into the six-fold symmetry of the crystal. The laws governing water molecules are rotationally symmetric. The ice crystal is not. In particle physics, the symmetry that is broken is called electroweak symmetry, the combined SU2 times U1 symmetry of the weak force and electromagnetism. At very high energies, this symmetry is intact, and the particles that carry the weak force and the electromagnetic force are all massless. Below a certain energy, the symmetry breaks. The photon, which carries the electromagnetic force, remains massless. The W and Z bosons, which carry the weak force, acquire mass, and the mechanism that gives them mass is the Higgs mechanism, involving a field that pervades all of space, called the Higgs field. The Higgs boson, the quantum of the Higgs field, was predicted in 1964 by Peter Higgs and independently by several other physicists. It was discovered in 2012 at the Large Hadron Collider at CERN, confirming the mechanism of symmetry breaking and completing the Standard Model. The discovery was announced on July 4, 2012 by two independent experimental teams, ATLAS and CMS, each with thousands of physicists, each analyzing data from billions of proton-proton collisions. The Higgs boson had been hiding for nearly 50 years, and finding it required the largest and most complex scientific instrument ever built. The Large Hadron Collider, a circular tunnel 27 kilometers in circumference beneath the Swiss-French border. Peter Higgs, who was 83 years old when the discovery was announced, wept during the presentation. He had proposed the mechanism in a two-page paper in 1964 and had spent his career defending a theoretical prediction that many physicists considered untestable. The discovery confirmed not just the existence of the Higgs boson, but the entire framework of spontaneous symmetry breaking. The idea that the universe's fundamental symmetries are hidden rather than absent, broken rather than destroyed. The discovery also confirmed a deeper principle, that the mathematical structure of symmetry groups, studied by pure mathematicians for reasons entirely unrelated to physics, correctly describes the fundamental structure of the physical universe. The mathematics came first and the particles came later. The symmetry groups predicted the particles before the particles were found. The discovery was the culmination of nearly 50 years of theoretical prediction and experimental effort, and it confirmed that the universe exists because symmetry is broken. The breaking of electroweak symmetry happened roughly 1/1,000,000,000th of a second after the Big Bang, when the temperature of the universe dropped below approximately 10 to the 15th degrees. Above this temperature, the W and Z bosons are massless and the electromagnetic force and the weak force are indistinguishable. Below this temperature, the Higgs field settles into its lowest energy state, the symmetry breaks, and the two forces become distinct. The universe you live in, with its massive W and Z bosons and its massless photon, is a consequence of this symmetry-breaking event in the first trillionth of a second of cosmic history. At even higher temperatures, earlier in the Big Bang, the strong force may have been unified with the electroweak force under a larger symmetry group. If so, this larger symmetry broke when the temperature dropped below roughly 10 to the 28th degrees, separating the strong force from the electroweak force. This event, called grand unification symmetry breaking, would have occurred roughly 10 to the negative 36th seconds after the Big Bang. The physics of that epoch is speculative, because the energies involved are far beyond what any accelerator can reach. But the mathematical framework of symmetry breaking provides the language for describing it. The ultimate symmetry breaking, if it occurred, would have separated gravity from the other three forces at even earlier times and even higher temperatures. The mathematics of this separation is not yet understood, because it requires a quantum theory of gravity that does not yet exist. But the pattern is clear. The history of the universe is a history of symmetry breaking, a cascade of phase transitions in which a single, highly symmetric initial state evolves into the complex, less symmetric universe we observe today. So the universe is built on symmetry, and the universe exists because symmetry is broken. Both statements are true. The laws have the symmetry. The solutions break it. The beauty of the mathematics is in the symmetry. The richness of the physical world is in the breaking. If you are drifting, let that paradox drift with you. Symmetry and its breaking, order and its violation, perfection and the departure from perfection that makes existence possible. The universe couldn't exist if the symmetries were perfect. It couldn't exist if they were absent. It exists in the space between, in the breaking, in the fall of the ball from the top of the hill. The concept of symmetry breaking appears not just in particle physics but throughout science and everyday experience. When you blow on a soap film stretched across a wire frame, the film bulges outward. The wire frame is symmetric, identical from both sides, but the soap film breaks the symmetry by bulging in one direction rather than the other. Which direction it bulges is random, determined by tiny air currents, but once it bulges, the symmetry is broken and the film has a preferred side. When water flows down a drain, it can spin clockwise or counterclockwise. The drain is symmetric. It has no preferred direction of rotation, but the water must choose one direction, and once it does, the symmetry is broken. The popular belief that water always spins one way in the northern hemisphere and the other way in the southern hemisphere is largely a myth for small drains where the Coriolis effect is negligible compared to residual currents. But the principle, symmetric system, asymmetric outcome, is correct. When a pencil is balanced on its tip, it has rotational symmetry. It can fall in any direction, but it must fall in some direction, and once it falls, the symmetry is broken. The laws of physics are symmetric. The pencil's final position is not. Phase transitions in material science are symmetry-breaking events. A liquid has rotational symmetry. It looks identical from every direction. When it freezes into a crystal, The crystal has only the discrete symmetries of its space group, a dramatic reduction in symmetry. Melting is the reverse, a restoration of symmetry. Boiling breaks the translational symmetry of the liquid into the disorder of the gas. The formation of galaxies in the early universe is a symmetry-breaking event. The early universe was nearly uniform, nearly symmetric, nearly identical in every direction. Small density fluctuations, amplified by gravity over billions of years, grew into galaxies, clusters, and the large-scale structure of the cosmos. The uniformity broke and the symmetry shattered, and the result is the universe you live in, with its galaxies and stars and planets and people, all of it a consequence of symmetry breaking on a cosmic scale. Symmetry appears not just in physics and mathematics, but in the living world, and the patterns of biological symmetry are among the most visible and most mysterious in nature. Most animals have bilateral symmetry, a single mirror line running from head to tail. The left side mirrors the right. This symmetry is so pervasive that exceptions are notable. Flatfish, which lie on one side, break bilateral symmetry. Fiddler crabs, with one enormous claw and one small one, break it. The human heart sits to the left of center, breaking the external bilateral symmetry of the torso. But the default, for virtually all animals with a front and a back, is bilateral. Why bilateral? The answer is connected to locomotion. An animal that moves in one direction needs a front and a back, a top where the eyes and brain are, and a bottom that touches the ground. Once you have a front, a back, a top, and a bottom, the only remaining symmetry is left-right, which is bilateral. Bilateral symmetry is the symmetry of directed motion. Evolution selected for it because a bilaterally symmetric body can be controlled by a simpler nervous system than an asymmetric body. Each muscle on the left has a corresponding muscle on the right, and the brain can coordinate them using symmetric neural circuits. The symmetry reduces the amount of genetic information needed to specify the body plan, because each gene that controls the left side also controls the right. Bilateral symmetry is efficient, both computationally and genetically. But no animal is perfectly bilaterally symmetric. The heart sits to the left. The liver sits to the right. The lungs have different numbers of lobes on each side. The internal organs break the external symmetry, and the breaking is not random. It is consistent across individuals of the same species. The gene that determines left-right asymmetry in vertebrates has been identified, and mutations in this gene can reverse the asymmetry, producing a condition called situs inversus, in which all the organs are mirror-reversed. The condition is rare and usually harmless because the reversed arrangement is just as functional as the normal one. The symmetry breaking doesn't matter much, as long as it's consistent. Animals that don't move much, like sea anemones and starfish, often have radial symmetry, multiple mirror lines radiating from the center. Animals that move in a definite direction are bilateral. The connection between bilateral symmetry and locomotion explains why jellyfish, which drift rather than swim in a directed way, have radial symmetry. It explains why sea urchins, which graze on the ocean floor without a definite front end, have five-fold radial symmetry. And it explains why sessile organisms, organisms that are permanently attached to a surface, like barnacles and coral polyps, often have radial symmetry because they encounter their environment equally from all directions and have no need for a front-back distinction. Viruses provide some of the most geometrically precise examples of symmetry in nature. Many viruses, including the common cold virus and the HIV virus, have icosahedral symmetry, the symmetry of a 20-sided regular solid. The protein coat of the virus is assembled from multiple copies of identical protein subunits, arranged with the symmetry of an icosahedron. The icosahedral symmetry allows the virus to build a large, sturdy shell from many copies of one small protein, minimizing the amount of genetic information needed to encode the shell. The symmetry is functional rather than aesthetic. It is a solution to an engineering problem found by evolution over billions of years. Plants show a different pattern. Flowers often have rotational symmetry, threefold in lilies, fivefold in roses, sixfold in lilies of the valley. The number of petals is usually a Fibonacci number, 3, 5, 8, 13, 21, and the arrangement follows a spiral pattern related to the golden ratio. The connection between flower symmetry and the Fibonacci sequence is one of the most visually striking examples of mathematics in nature, and the explanation involves the geometry of growth, the angle at which new cells are added to a growing tip, which is related to the golden angle, roughly 137.5 degrees, which is related to the golden ratio, which is related to the Fibonacci numbers. The Fibonacci connection to flower symmetry is worth pausing on because it illustrates how symmetry connects to number theory through geometry. The Fibonacci numbers 1, 1, 2, 3, 5, 8, 13, 21, 34 are generated by a simple rule: each number is the sum of the two preceding numbers. The sequence was described by Leonardo of Pisa, known as Fibonacci, in 1202 in the context of a problem about rabbit populations. The ratio of consecutive Fibonacci numbers converges to the golden ratio, approximately 1.618. The golden ratio has a geometric property that connects it to spirals. If you tile a plane with squares whose side lengths follow the Fibonacci sequence, the corners of the squares trace a spiral that approximates a logarithmic spiral with growth factor equal to the golden ratio. This spiral appears in the arrangement of seeds in a sunflower head, in the scales of a pine cone, in the florets of a cauliflower, and in the leaves on a stem. The reason is that the golden angle, approximately 137.5 degrees, is the most irrational angle, the angle that is hardest to approximate by simple fractions. When a plant adds new cells at this angle, the cells pack as efficiently as possible, filling space without leaving large gaps. The Fibonacci symmetry of plants is not an accident. It is a solution to an optimization problem found by evolution over hundreds of millions of years. The connection runs from number theory, through the golden ratio, through the geometry of spirals, through the biology of plant growth, and back to symmetry, because the spiral patterns of seeds and leaves exhibit a specific rotational quasi-symmetry that is directly related to the irrationality properties of the golden ratio. Numbers, geometry, biology, and symmetry, linked by one constant and one growth rule. The snowflake we started with has six-fold symmetry, because water molecules bond at angles that naturally produce hexagonal arrangements when the molecules crystallize. The six-fold symmetry of ice is a consequence of the geometry of the water molecule. Two hydrogen atoms bonded to one oxygen atom at an angle of roughly 104.5 degrees. When millions of these molecules stack together, the hexagonal symmetry of the individual bonds produces the six-fold symmetry of the macroscopic crystal. Every snowflake has six-fold symmetry, yet no two snowflakes are identical. The symmetry is universal, but the details are unique. The six-fold pattern is determined by physics, by the bond angles of water. The specific branching pattern is determined by the temperature, humidity, and air currents that each snowflake encounters as it falls. The symmetry constrains what is possible, and the details record what actually happened. The search for the symmetry group of gravity, the fourth fundamental force, is one of the great open problems in theoretical physics. The three forces described by the Standard Model, electromagnetism, the weak force, and the strong force, are all gauge theories with specific symmetry groups. Gravity, described by Einstein's general relativity, is also a theory with deep symmetry properties. It is invariant under general coordinate transformations, the most general possible symmetry of spacetime. But the quantization of gravity, the construction of a quantum theory that combines general relativity with quantum mechanics, has resisted all attempts for nearly a century. String theory, the leading candidate for a quantum theory of gravity, proposes that the fundamental objects are not point particles but one-dimensional strings. The symmetries of string theory are vastly larger than the symmetries of the Standard Model, involving not just the gauge groups of particle physics, but the symmetries of the extra dimensions of space that string theory requires. Different versions of string theory have different symmetry groups, and the relationships between the versions, called dualities, are themselves symmetry transformations. The web of dualities connecting different string theories was elucidated in the 1990s, primarily by Edward Witten, who proposed that all 5 consistent string theories are different limits of a single 11-dimensional theory called M theory. The symmetries of M theory are not fully understood, but they are believed to include the exceptional Lie group E8, the monster group through Moonshine connections, and possibly symmetries that have not yet been identified. Whether string theory correctly describes nature is an open question. The theory has not made any testable predictions that have been confirmed by experiment. But the mathematical structure of the theory, the richness of its symmetries, the depth of its connections to pure mathematics, has produced results in topology, algebraic geometry, and number theory that would not have been discovered by any other route. String theory may or may not be physics. It is certainly mathematics, and the mathematics is driven by symmetry. The story of symmetry in physics is a story of progressive unification. Newton unified terrestrial and celestial mechanics through the symmetry of universal gravitation. Maxwell unified electricity, magnetism, and light through the symmetry of gauge invariance. Einstein unified space and time through the symmetry of Lorentz invariance. The Standard Model unified three forces through the symmetry of its gauge group, and the dream of a final theory, a theory that unifies all forces and all particles in a single mathematical framework, is a dream of a single symmetry group from which everything follows. Whether that dream is achievable, whether the universe has a single master symmetry that determines all of its laws and all of its particles, is unknown. But the progress from Newton to the Standard Model, a progression driven at every step by the identification and exploitation of symmetry, suggests that the dream is not unreasonable. The universe has rewarded the search for symmetry at every stage. There is no reason to think it will stop. The relationship between symmetry and beauty is not just a Greek intuition. Psychological research has confirmed that humans have an innate preference for symmetric faces, symmetric bodies, and symmetric patterns. The preference appears in infants as young as 4 months old, long before any cultural conditioning could take effect. Babies look longer at symmetric faces than at asymmetric ones, suggesting that the preference for symmetry is built into the human perceptual system. The evolutionary explanation is that symmetry signals developmental health. An organism that grows symmetrically has resisted the perturbations of disease, parasites, and environmental stress that tend to disrupt symmetry. A symmetric face or body is, on average, a healthier face or body. The preference for symmetry evolved because choosing a symmetric mate increased the likelihood of choosing a healthy one. This evolutionary explanation connects the Greek association of symmetry with beauty to modern biology. The Greeks were right that symmetry is beautiful, and they were right that beauty reflects something real, something about the quality of the thing being admired. They just didn't know the mechanism. The mechanism is evolution, operating over millions of years, embedding a preference for symmetry into the neural circuitry of the human brain. The preference for symmetry extends beyond faces and bodies. People prefer symmetric designs, symmetric buildings, symmetric gardens, symmetric musical compositions. The preference is not absolute. Perfect symmetry can feel static and lifeless. The most admired works of art and architecture often combine strong symmetry with subtle asymmetry, a dominant symmetric structure with small departures that add interest and vitality. The Parthenon's entasis, the slight asymmetries in a handcrafted ceramic bowl, the rubato in a musical performance, all break the symmetry just enough to make the symmetric structure feel alive. The relationship between symmetry and beauty in mathematics is different, but related. Mathematicians frequently describe their results as beautiful, and the results they call beautiful are almost always characterized by symmetry, by an unexpected simplicity, by a unification of apparently different things. Euler's identity is called beautiful because it unifies 5 constants through a single symmetric equation. Noether's theorem is called beautiful because it unifies conservation laws and symmetries through a single principle. The Galois correspondence is called beautiful because it maps the structure of one mathematical world perfectly onto the structure of another. The mathematician G.H. Hardy wrote that the mathematician's patterns, like the painter's or the poet's, must be beautiful. The ideas, like the colors or the words, must fit together in a harmonious way. Beauty is the first test. There is no permanent place in the world for ugly mathematics. Hardy's criterion of beauty is, at its core, a criterion of symmetry, of harmony, of the fitting together of parts into a coherent whole. Symmetry appears in music as well. A melody played backward is a retrograde. A melody flipped upside down, with ascending intervals becoming descending intervals, is an inversion. A melody played backward and upside down is a retrograde inversion. These four transformations, original, retrograde inversion, and retrograde inversion, form a group with four elements called the Klein-4 group. Johann Sebastian Bach used all four transformations in his fugues, rotating and reflecting melodic themes with a mathematical precision that modern group theorists recognize as formal symmetry operations. Bach didn't know group theory. Group theory wouldn't be invented for another century. But he understood intuitively and completely the symmetries available to a melodic line, and he exploited them with a thoroughness that no composer before or since has matched. The 12-tone technique, developed by Arnold Schoenberg in the early 20th century, uses the same four transformations applied to a fixed sequence of all 12 notes of the chromatic scale. The technique treats the 12-tone row as a mathematical object and manipulates it using the Klein-4 group, producing a musical structure that is as much algebra as art. Whether the result is beautiful is debated. That it is symmetric is not. Now we turn to the largest and most mysterious symmetry group in mathematics, a mathematical object so vast and so strange that the mathematicians who discovered it named it the monster. The finite simple groups are the building blocks of all finite symmetry groups, the way prime numbers are the building blocks of all integers. Every finite group can be built from simple groups through a process analogous to factoring a number into primes. The classification of all finite simple groups, completed in the early 1980s, is one of the longest proofs in the history of mathematics, spanning tens of thousands of pages across hundreds of journal articles written by over 100 mathematicians over a period of roughly 30 years. The classification revealed that most finite simple groups fall into well-understood infinite families, analogous to the way most primes follow the general distribution predicted by the prime number theorem. But there are 26 exceptions, 26 sporadic simple groups that don't belong to any infinite family. They just exist, isolated, unexplained, each one a finite symmetry group that doesn't fit into any pattern. The smallest sporadic group, called M11, has 7,920 elements. The second smallest, M12, has 95,040. The names come from Émile Mathieu, who discovered the first 5 sporadic groups in the 1860s. The remaining 21 were discovered over the following century, the last few requiring computer assistance to verify their existence and properties. The 26 sporadic groups are one of the great mysteries of mathematics. Why do they exist? Why are there exactly 26? What do they have in common? Nobody knows. The classification of finite simple groups tells us that these are all the sporadic groups there are, but it doesn't explain why they exist or why they have the sizes and structures they do. They are mathematical facts without mathematical explanations, objects that exist because logic permits them, but for no deeper reason that anyone has found. The classification of finite simple groups, sometimes called the enormous theorem, is one of the largest collaborative mathematical achievements in history. The proof, assembled over roughly 30 years from the 1950s to the early 1980s, involves contributions from more than 100 mathematicians across dozens of institutions. The combined length of the proof is estimated at 10,000 to 15,000 pages, spread across hundreds of journal articles, making it by far the longest proof in the history of mathematics. Between the continuous Lie groups and the finite groups, there is a bridge. The groups of Lie type, finite groups that are constructed from Lie groups using techniques from algebraic geometry over finite fields. These groups account for most of the finite simple groups in the classification theorem. They include familiar objects like the general linear group of n by n invertible matrices, with entries in a finite field, and less familiar objects like the Chevalier groups and the twisted groups of Steinberg, Ree, and Suzuki. The construction of groups of Lie type reveals that the division between finite and continuous symmetry is not as sharp as it first appears. The same Lie-theoretic structures that produce continuous symmetry groups when applied over the real or complex numbers produce finite symmetry groups when applied over finite fields. The mathematics is the same. The number system changes, and the change from infinite to finite produces new groups with their own distinctive properties, groups that are neither purely continuous nor purely discrete, but somewhere in between. This bridge between finite and continuous mathematics is one of the great themes of modern algebra. It connects number theory to geometry, algebra to analysis, the discrete to the continuous, and it runs through symmetry, through group theory, through the mathematical framework that Galois created and that Lie extended and that the 20th century applied to the fundamental structure of matter and energy in space-time. The theorem states that every finite simple group is either one of the well-understood infinite families, the cyclic groups of prime order, the alternating groups, the groups of Lie type, or one of the 26 sporadic groups. The classification is complete. There are no other finite simple groups waiting to be discovered. The theorem is the ultimate classification result for symmetry, a complete enumeration of all the fundamental building blocks from which all finite symmetry groups can be constructed. The proof has been checked and rechecked, but its length makes verification difficult. A project to produce a simplified, streamlined proof called the GLS project after its leaders, Daniel Gorenstein, Richard Lyons, and Ronald Solomon, has been underway since the 1980s. The simplified proof is expected to run to roughly 5,000 pages, a significant reduction from the original, but still extraordinarily long by mathematical standards. The existence of the sporadic groups remains one of the great mysteries of mathematics. The infinite families of finite simple groups are well understood. They arise from Lie groups over finite fields, a construction that is natural and well motivated. The sporadic groups arise from no such construction. They simply exist, each one a unique mathematical object with properties that don't fit any general pattern. The monster group, the largest sporadic group, has been called the most beautiful thing in mathematics by some mathematicians and an embarrassment by others, an isolated behemoth whose existence seems arbitrary, a mathematical fact without a mathematical reason. Whether the sporadic groups have a deeper explanation, a unifying principle that accounts for their existence and their properties, is an open question. The Moonshine connection to modular forms and string theory hints at such an explanation, but nobody has found it. The classification of finite simple groups is, in a sense, the classification of all possible finite symmetries. It tells you everything that symmetry can be, at least in the finite case, and the list is surprisingly short. A few infinite families and 26 exceptions. The world of finite symmetry, which seems at first to be unlimited in its variety, turns out to be tightly constrained. Only certain symmetries are possible, and the possible symmetries are completely known. The largest of the sporadic groups is the monster, discovered in the 1970s. The monster has roughly 8 times 10 to the 53rd elements, a number so large that writing it in full would take 54 digits. The monster is a symmetry group, meaning it is the set of symmetries of some mathematical object, but the object, it is the symmetries of lives in a space of 196,883 dimensions. The monster is the symmetry group of an object that no human will ever visualize, in a space that no human will ever see, and it exists as surely as the symmetries of a square. The monster connects to seemingly unrelated parts of mathematics through monstrous moonshine, a connection between the monster group and the theory of modular forms that was so unexpected that it was initially dismissed as coincidence. The mathematician John Mackay noticed in 1978 that certain numbers associated with the monster matched certain numbers from the theory of modular functions, functions that come from complex analysis and number theory. The match was too precise to be accidental. Richard Borchards proved in 1992 that the connection is real and exact, using techniques from string theory, and received the Fields Medal for the proof. The monster group connects algebra to complex analysis to theoretical physics through a chain of relationships that nobody anticipated and that nobody fully understands. It is the largest known example of the pattern we've been tracing throughout this story, that different parts of mathematics developed independently for different reasons by different people, turn out to be connected through structures that nobody designed and that nobody expected. The concept of symmetry also illuminates the foundations of mathematics itself. In the early 20th century, Felix Klein proposed what became known as the Erlangen program, a vision for unifying geometry by classifying geometries according to their symmetry groups. Euclidean geometry, Klein argued, is the study of properties preserved by the Euclidean group, the group of rotations, reflections, and translations. Affine geometry is the study of properties preserved by the larger affine group, which includes shearing and scaling. Projective geometry is the study of properties preserved by the even larger projective group, which includes perspective transformations. Each geometry corresponds to a symmetry group, and the hierarchy of geometries corresponds to the hierarchy of groups. Klein's program didn't just organize existing geometries, it revealed new ones. Any group of transformations defines a geometry, the geometry of properties preserved by that group. This insight opened the door to geometries that had never been studied, geometries defined by symmetry groups that had no classical counterpart. The program transformed geometry from a collection of separate subjects into a unified framework organized by symmetry, and it influenced the development of mathematics throughout the 20th century. The Erlangen program also influenced physics. Einstein's special relativity can be understood as the geometry defined by the Lorentz group, the group of transformations that preserve the spacetime interval. General relativity can be understood as the geometry defined by the group of all smooth coordinate transformations. In both cases, the physics is determined by the symmetry, and the symmetry is captured by a group, exactly as Klein's program proposed. The connection between Klein's program and modern physics was not coincidental. Klein was one of the most influential mathematicians of his generation, and his ideas about symmetry and geometry shaped the education of the physicists who would later develop relativity and quantum mechanics. The mathematical framework was ready when the physics needed it because Klein and his students had built it in advance. Symmetry also plays a central role in the philosophy of mathematics. The question of whether mathematical objects are discovered or invented, whether they exist independently of human minds or are human constructions, is one of the oldest questions in philosophy. Symmetry provides evidence for the discovery view because identical symmetry groups keep appearing in different contexts, discovered independently by different people, suggesting that they have an existence independent of any particular discovery. The 17 wallpaper groups were explored by Islamic artisans and proved by Russian crystallographers. The Lie groups were discovered by a Norwegian mathematician and applied by German physicists. The monster group was constructed by algebraists and connected to string theory by physicists. In each case, identical mathematical object appeared in completely different contexts, discovered by people who had no knowledge of each other's work. The convergence suggests that the objects are real, that they exist in a mathematical universe that humans explore but do not create. Whether this argument is convincing depends on your philosophical commitments. A formalist would say that the convergence reflects common axioms, not common objects. A constructivist would say that the objects are constructed by human mathematical activity, and the convergence reflects common cognitive structures. A Platonist would say that the objects exist independently and that humans discover them, the way astronomers discover stars. The debate is unresolved and may be unresolvable, but symmetry, more than any other mathematical concept, makes the Platonist position tempting. The practical applications of symmetry in everyday technology are so pervasive that they are invisible. The compression algorithms that reduce the size of digital images exploit symmetries in the data, patterns that repeat across the image. The error-correcting codes that protect data during transmission exploit the algebraic symmetry of polynomial rings over finite fields. The fast Fourier transform, which is used in virtually every digital signal processing application, exploits the symmetry of the roots of unity, the complex numbers that are equally spaced around the unit circle. Every time you listen to digital music, the signal has been compressed using algorithms that exploit frequency domain symmetry through the Fourier transform. Every time you make a phone call, the voice signal is encoded using error-correcting codes based on the algebraic structure of finite groups. Every time you use GPS, the position is calculated using signals from satellites whose orbits are solutions to differential equations with rotational symmetry. The technology is invisible, but the symmetry is everywhere. The mathematician and physicist Freeman Dyson once divided mathematics into two cultures: the birds, who survey the landscape from above, seeing connections and patterns, and the frogs, who explore the details of specific problems close to the ground. Symmetry is a bird concept. It surveys the landscape of mathematics from above and sees connections that the ground-level view misses. It connects algebra to geometry, geometry to physics, physics to cosmology, cosmology to philosophy. It is the thread that runs through the entire tapestry of mathematical thought, from the Greek temples to the Large Hadron Collider, from the Alhambra tiles to the monster group, from the snowflake to the Big Bang. The concept of chirality, or handedness, is a specific type of symmetry breaking that has profound consequences in chemistry and biology. Your left hand and your right hand are mirror images of each other. They have identical structure but cannot be superimposed. No matter how you rotate your left hand, you cannot make it match your right hand exactly. This property, the non-superimposability of an object with its mirror image, is called chirality. Many molecules are chiral. They exist in two mirror image forms called enantiomers that are chemically identical in most respects but behave differently in interactions with other chiral molecules. The amino acids that make up proteins are almost exclusively left-handed. The sugars in DNA are almost exclusively right-handed. This homochirality, the exclusive use of one-handedness, is one of the most fundamental characteristics of life on Earth, and nobody knows how it arose. The laws of physics, at the level of electromagnetism and the strong force, are symmetric under reflection. They don't prefer left over right. But the weak force, the force responsible for radioactive decay, violates this symmetry. The weak force distinguishes between left-handed and right-handed particles. This violation of mirror symmetry, called parity violation, was discovered experimentally by Chen-Xiong Wu in 1957 in one of the most important experiments in the history of physics. Wu's experiment showed that cobalt-60 nuclei, aligned by a magnetic field and cooled to near absolute zero, emit electrons preferentially in one direction during beta decay. The emission pattern is not symmetric under reflection. The weak force, alone among the fundamental forces, knows the difference between left and right. Whether the parity violation of the weak force is connected to the homochirality of biological molecules is an open question. The energy difference between left-handed and right-handed amino acids, calculated from the weak force, is extraordinarily small, roughly 10 to the negative 17 of the total energy. Whether this tiny difference is enough to tip the balance over billions of years of prebiotic chemistry is debated. Some scientists believe it is. Others believe that the homochirality of life arose from a random fluctuation, amplified by autocatalytic processes that locked in one-handedness once it became dominant. The question connects particle physics to the origin of life through the concept of symmetry breaking. The connection between symmetry and information is another thread worth following. Claude Shannon's information theory, which quantifies the information content of messages and the capacity of communication channels, has deep connections to symmetry through the concept of entropy. Shannon entropy measures the uncertainty of a message source, the average amount of information per message. A source that produces messages with uniform probability has maximum entropy, maximum uncertainty, maximum information per message. This maximum entropy state is also the most symmetric state, the state in which all messages are equally likely and no message is preferred over any other. The maximum entropy principle, developed by Edwin James in the 1950s, says that when you have incomplete information about a system, you should assume the probability distribution with the highest entropy consistent with your constraints. This principle produces the most symmetric, the least biased, the most honest distribution given what you know. The principle connects information theory to statistical mechanics, because the probability distributions of statistical mechanics, the Boltzmann distribution, the Fermi-Dirac distribution, the Bose-Einstein distribution, are all maximum entropy distributions subject to different constraints. The connection between symmetry and entropy runs even deeper. The entropy of a physical system is related to the number of microstates consistent with the observed macrostate, and this number is determined by the symmetry group of the system. A system with more symmetry has more microstates and higher entropy. Breaking a symmetry reduces the number of microstates and reduces the entropy. The second law of thermodynamics, which says that entropy never decreases in an isolated system, can be understood as a statement about the tendency of systems to explore all available microstates, which is a tendency toward maximum symmetry. Symmetry, entropy, information, and thermodynamics are four perspectives on one underlying mathematical structure. The connections between them are exact and bidirectional, and they run through group theory, through information theory, through statistical mechanics, through the deepest levels of mathematical physics. The deepest question about symmetry is whether the symmetries of the universe are fundamental or emergent. If the symmetries are fundamental, they are built into the fabric of reality at the deepest level, and the laws of physics are consequences of these symmetries. If the symmetries are emergent, they arise from a deeper, possibly non-symmetric structure, the way the circular symmetry of a whirlpool arises from the non-symmetric motions of individual water molecules. The distinction matters because it determines how physicists search for new theories. If symmetry is fundamental, the path forward is to find larger, more encompassing symmetry groups, grand unified theories. Supersymmetry, the symmetries of string theory. If symmetry is emergent, the path forward is to find the deeper structure from which the observed symmetries arise, a structure that might not be symmetric at all. Most physicists currently believe that at least some symmetries are fundamental. The gauge symmetries of the Standard Model appear to be exact symmetries of nature, not approximate or emergent, but the question is open, and the answer may depend on which symmetries you're asking about. Space-time symmetries like Lorentz invariants might be fundamental. Internal symmetries like gauge invariants might be emergent, or vice versa. The distinction is one of the central questions of 21st century physics. The mathematician and physicist John Wheeler proposed that the ultimate theory of physics might be based not on symmetry but on information, on the principle he called it from bit. In Wheeler's vision, the fundamental stuff of the universe is not matter or energy or space-time, but information, and the laws of physics, including their symmetries, emerge from the information-theoretic structure of reality. Whether this vision is correct or even coherent is debated, but it represents an alternative to the symmetry-based approach that has dominated fundamental physics for a century, and it suggests that the deepest explanations may lie beyond symmetry, in territory that mathematics has not yet mapped. The question remains open. Symmetry has been the most powerful organizing concept in the history of physics, the concept that unified forces, predicted particles, explained conservation laws, and classified the fundamental constituents of matter. Whether symmetry is the final word, or merely the most successful chapter in a longer story, is a question for the next generation of mathematicians and physicists to answer. The medieval Islamic contribution to the mathematics of symmetry extends beyond the Alhambra. Islamic mathematicians and artisans developed the Galois tiles, a set of 5 tile shapes that can produce complex non-repeating patterns with local 5-fold symmetry. These patterns, found on the Darbai Imam shrine in Isfahan, Iran, dating from 1453, anticipate Penrose tilings by over 500 years. The physicist Peter Liu and the mathematician Paul Steinhardt analyzed the Galois patterns in a 2007 paper and showed that the medieval artisans had discovered quasi-crystalline tilings centuries before the mathematical theory existed. The artisans may not have understood the mathematics. They may have used purely aesthetic criteria to select the patterns, but the mathematics was there, embedded in the tiles, waiting to be discovered. The Islamic tradition of geometric art also produced the muqarnas, 3-dimensional decorative vaults composed of hundreds or thousands of small, niche-like elements arranged in precise geometric patterns. The muqarnas of the Hall of the Ambassadors in the Alhambra, a dome composed of over 8,000 individual cells arranged in concentric tiers, represents one of the most complex 3-dimensional geometric structures ever built by hand. The structure has a specific symmetry group, a subgroup of the 3-dimensional space groups, and its construction required an understanding of 3-dimensional geometry that rivals anything in contemporary European mathematics. The Islamic mathematical tradition, which flourished from roughly the 8th to the 15th centuries, made fundamental contributions to algebra, trigonometry, and geometry. The word algebra comes from the Arabic al-jabra, meaning restoration, from the title of al-Khwarizmi's foundational text. The word algorithm comes from al-Khwarizmi's name. The Islamic contribution to the mathematics of symmetry, expressed through art rather than through theorems, is one of the most remarkable episodes in the history of mathematics, a case where aesthetic intuition reached mathematical truth centuries before formal proof caught up. The Rubik's Cube, invented by the Hungarian architect Ernie Rubik in 1974, is one of the most familiar examples of group theory in everyday life. The possible states of the cube form a group, the Rubik's Cube group, with approximately 43 quintillion elements, roughly 4.3 times 10 to the 19th. Each move, each quarter turn of a face, is a group element, and solving the cube means finding a sequence of group elements that transforms the scrambled state into the solved state. The mathematical analysis of the Rubik's Cube has revealed deep structural properties. The group can be decomposed into smaller groups corresponding to specific aspects of the cube's structure. The positions and orientations of the corner pieces, the edge pieces, and the center pieces. The optimal solution, the minimum number of moves needed to solve any scrambled state, was proved in 2010 to be at most 20. This number, sometimes called God's number, was determined by a computer search that analyzed every possible position, roughly 43 quintillion of them, using the symmetries of the group to reduce the computation to manageable size. The Rubik's Cube illustrates several key principles of group theory: the decomposition of a complex group into simpler components, the use of symmetry to simplify computations, and the relationship between abstract algebra and physical manipulation. It is also, not incidentally, one of the best-selling toys in history, with over 450 million cubes sold worldwide. Group theory has never had a better marketing department. The mathematical puzzle community has explored many variations: cubes of different sizes, dodecahedral puzzles, pyramidal puzzles with different numbers of layers. Each variation has its own group, and the properties of the group determine the difficulty and the character of the puzzle. The 2x2 cube has roughly 3.7 million states. The 4x4 cube has roughly 7.4 times 10 to the 45th. The groups grow rapidly, but the group theoretic tools for analyzing them remain the same. The supersymmetry hypothesis proposed in the 1970s extends the symmetry of the Standard Model by relating bosons, the force-carrying particles, to fermions, the matter particles. In a supersymmetric theory, every boson has a fermionic partner, and every fermion has a bosonic partner. The symmetry that relates them is called supersymmetry, and it is a symmetry of a new type, a symmetry that relates particles with different spin, a property that determines how particles behave under rotations. Supersymmetry, if it exists, would solve several outstanding problems in physics. It would explain why the Higgs boson has the mass it does, protecting it from quantum corrections that would otherwise drive it to an absurdly large value. It would provide a candidate for dark matter, the invisible substance that makes up roughly 27% of the universe's mass-energy content, and it would bring the strengths of the three Standard Model forces closer together at high energies, supporting the idea that they unify into a single force. Despite these theoretical motivations, supersymmetry has not been observed experimentally. The Large Hadron Collider has searched for supersymmetric particles at energies up to several trillion electron volts without finding them. The absence of evidence does not prove that supersymmetry is wrong. The supersymmetric partners might simply be too heavy for the current accelerator to produce, but the absence has made many physicists less confident that supersymmetry is a feature of nature rather than a feature of mathematics. The fate of supersymmetry is one of the most important open questions in physics. If it is found, it will represent the largest extension of symmetry since the Standard Model was completed. If it is not found, it will force physicists to reconsider the role of symmetry in fundamental physics and to seek alternative explanations for the problems that supersymmetry was designed to solve. The deepest symmetry of all may be the symmetry between mathematics and physics themselves. The physicist and mathematician Eugene Wigner observed that mathematical structures, invented for purely abstract reasons, repeatedly turn out to describe physical reality with extraordinary precision. Group theory, invented to study equations, describes elementary particles. Riemannian geometry, invented to study curved spaces, describes gravity. Hilbert spaces, invented to study infinite-dimensional linear algebra, describe quantum mechanics. The correspondence between mathematical structure and physical reality is so consistent and so precise that it demands an explanation, and no satisfying explanation has been found. Wigner called it the unreasonable effectiveness of mathematics, and the adjective unreasonable is carefully chosen. The effectiveness of mathematics in describing nature goes beyond what any reasonable account of the relationship between abstract thought and physical reality can explain. The symmetry-based approach to physics has been so successful that some physicists have proposed elevating symmetry from a tool to a principle, arguing that the fundamental laws of nature are determined entirely by their symmetries. In this view, the standard model is not discovered by experiment, but derived from the requirement that the laws of physics be invariant under specific symmetry transformations. The experiments confirm the derivation, but the logic runs from symmetry to physics, not from physics to symmetry. Whether this view is correct, whether symmetry is the foundation of physics rather than merely a feature of it, is one of the deepest questions in the philosophy of science. The history we've traced tonight, from snowflakes to the standard model, suggests that symmetry runs very deep indeed, deeper than any other organizing concept in either mathematics or physics. Whether it runs all the way down, whether symmetry is the bedrock on which everything else rests, is a question for the future. The physicist David Gross, who received the Nobel Prize for his work on the strong force, has said that the most important lesson of 20th century physics is that symmetry dictates interaction. The forces of nature are not arbitrary, they are consequences of symmetries, and the symmetries are not arbitrary either. They are members of a small, classified, completely enumerated family of mathematical structures. The universe is built from a short list of symmetries, and the list is known. The snowflake falls. Its 6 sides reflect the hexagonal symmetry of crystallized water. The crystal is held together by electromagnetic forces, whose symmetry group is U1. The protons and neutrons in its oxygen nucleus are held together by the strong force, whose symmetry group is SU3. The radioactive decay of a carbon-14 atom in the snow nearby is governed by the weak force, whose symmetry group is SU2. 3 forces, 3 symmetry groups, 1 snowflake, falling through cold air toward a ground it will never consciously reach. We started with a snowflake. 6 sides, always 6, the symmetry determined by the bond angles of water molecules crystallizing in the cold. We followed symmetry from the Greek temples where it meant beauty, through the Islamic palaces where it became art, through the prison cell where a 20-year-old French mathematician transformed it into algebra, through the theorem that links it to every conservation law in physics, through the standard model where it organizes every known particle and force, through the breaking that makes the universe possible, through the living world where it shapes flowers and animals and crystals, and into the monster, the largest sporadic simple group lurking in a space of 196,000 dimensions, connected by moonshine to functions in complex analysis. Symmetry is not a property, but a principle. It is the organizing principle of geometry, of algebra, of physics, of biology, and of the deepest structures in abstract mathematics. Everything that is regular is symmetric. Everything that is conserved is symmetric. Everything that is classifiable is classified by its symmetries, and the mathematics of symmetry, group theory, invented by a 20-year-old who died before he could explain it, is now the language in which the fundamental structure of reality is written. The symmetries are still there. They were there before Noether proved her theorem, before Galois wrote his letter, before the artisans of the Alhambra laid their first tile. The conservation of energy holds tonight as it held last night, and as it will hold tomorrow, because the laws of physics do not change over time, and Noether's theorem guarantees the rest. The mathematics was there before anyone wrote it down. The 6-fold symmetry of ice is as old as water. The 17 wallpaper groups are as old as flat surfaces. The 230 space groups are as old as 3-dimensional space. The symmetry groups of the standard model are as old as the forces they describe, which is to say they are as old as the universe. Symmetry is not a human invention. It is a discovery, something that was always there, waiting to be noticed. Galois noticed part of it in a prison cell at 20. Noether noticed a deeper part at Göttingen, against the opposition of an entire university that didn't want her there. The artisans of the Alhambra noticed it 6 centuries before anyone proved it, and the snowflake has been exhibiting it for 4.5 billion years, since the first water froze on the first cold night of the young Earth. And the mathematics, as always, was there before anyone wrote it down, and that is more than enough to carry into sleep.